Hello guys, so let's talk about construct binary tree from preorder and inorder traversal. So given two integer arrays, preorder and inorder, where preorder is the preorder traversal of a binary tree and inorder is the inorder traversal of the same tree, construct and return is binary tree. So you are basically you are given a tree and you will give it two array. One is preorder, the other one is inorder. So preorder is you go over yourself first and left and right subtree later. And inorder is you go your left first and then yourself and right. So you will get to this array. So I'm gonna show you a diagram how the preorder and inorder build based on the array. So you are given the you are going to have a root value in the beginning for your preorder no matter what, and inorder is like somewhere in the between of root.left and root.right. So whatever you go through the preorder, you'll find it in inorder. So the size of the root.left is equal to from the inorder is equal to the preorder's root.left, and same as root.right in order is equal to preorder root.right. So they just code it so you will see the idea. So I will have a helper function, definitely public tree node, and I'm going to say build tree no matter what. So I do have the preorder in a preorder array and preorder star and preorder n. Okay, so this is two main important stuff for preorder index, and same as inorder, and then I have the inorder star and inorder n. So what you actually need to do is just return build tree and then preorder and 0 to preorder dot length -1 and then comma, and inorder same things, inorder dot length -1. Okay, so whatever you build from this helper function, this is really important. So what I will do is let's talk about the root value. So the value for root is the beginning preorder dot index 0, which is preorder star, right? So I set equal to 0 at the beginning, right? Then I need to know what is the index inorder when the root value occur in the preorder array. So for int I equal to 0, I less than inorder, actually it's not 0, sorry. It start from inorder dot start, sorry, and end with inorder dot length, and sorry, a plus plus. So I'm going to find the root value if inorder at I is equal to root val. Then you set the index equal to I and then you break. This is actually how you find the index root value in the inorder. So let me just repeat again. I set the index, that variable for inorder, to find the value for the root value, to find the root value in the inorder array. So I start from inorder star. So don't start from 0. When you cut into the half to find on your left subtree and right subtree, it's not actually start from 0. You start from where you actually split. So inorder star to inorder n, and then you have the check condition in inorder I is equal to the root value, then you set the index. Now we can actually know what happened for the tree node root equal to new tree node. So we can actually know the root value is equal to the root value. And we have the root.left and we do have the root.right. So root.left and root.right is using the recursion idea So I do have a build tree, and I do have preorder array, and I'm going to skip the preorder index first. Then I do have a Inorder. So if you split the Inorder index for the left subtree, didn't you just do the Inorder star to the index you found, and then what do you actually need to do? +1 or -1? Should be -1, right? Because we already know the root value is equal to the tree root. And same thing for the preorder. And I'm going to skip the preorder index. And to the right is index +1, and in order n. This is how you actually know where you actually need to split on your left subtree and right subtree. Now let's talk about preorder. So we do have to know there is okay, so I just closed the picture, but the preorder is like this. You have the root val, and then after that is root dot left, after that is root dot right? And in order is simple, is root dot left first, root val, and root dot right. This is how you actually do, right? So we already know the root value, right? So we can actually know the size of the root dot left. How do you actually do it? Is here. Its size, okay, I'm going to call left size is equal to the index. Index is at this position, right? Index minus Inorder star, right? Why do I have to minus the Inorder star? Because when you cut into the half, right, it won't be a 0 every single time. So I mean, where you actually split, this is how you actually know the size of the left, and we can actually know. So preorder is actually becomes preorder, right? Preorder star +1 to over here, right? So how do you actually know what's the index over there? So I'm going to say preorder pre-star. Okay, so this is root dot left, right? So preorder star and +1, because we already take away the root value, right? So you start from preorder star +1 to preorder star plus left size. So you get the idea, right? This is how you actually split. So +1, you start from here, and so you have to know the size of the root dot left is preorder star plus left size. So including root value, we do have the same length for the root dot val plus root dot left. So the idea will be similar to root dot right. So root dot right will become where you actually end. So pre-star, where do I just start? So pre-star plus left size +1, right? So we continuous on the left subtree. Continuous on the left subtree to the right subtree. So where do you actually end? Just pre-end. This is simple. And at the end, you just return root. But beforehand, we need a base case because we keep calling yourself, right? So that would be if I'm going to say pre-star. If pre-star is greater than pre-end, you just return null. So we know where we actually need to stop. And let's see, do I have an error or not? Okay, I do have error. So probably tree null. Yeah, tree null. Okay. Okay, I do have another preorder star. Okay. Preorder star, preorder n. I'm going to see, do I have typo? Yes, preorder n and preorder star. Sorry, making typo. Inorder star, index, Inorder. Okay, let's just run it again. And hopefully, yes, I pass. and should be good, right? So let's talk about time and space. So how many times you visit in array? You only visit once, right? So if you break out, if you meet this condition, you just break. I mean, you return the node and then you start backing up. So the time is all of n, space is all of n, right? Because you build a tree only once, not the twice, not the third, right? So that would be the time and space complexity, all of n for both. So that would be the solution, and good luck.